Hello, my name is Ravi Peters and I am from the 3D Geoinformation group at TU Delft. I will be talking about the generation of a 3D model of the Netherlands, a project that we did in cooperation with the Dutch Kadaster. To begin, I will show you a screenshot of our model, and as you can see it is really a complete model of our country, including not only the buildings, but also roads, water bodies and terrain. Now, why do we want a national 3D model? Firstly, we observe that 3D data is increasingly generated and used by local governments such as municipalities. However, this is not done by all local governments and not in a consistent manner. Secondly, we have the opportunity to support governmental decision processes on a wider level by integrating the 3D city model more tightly with existing national data infrastructure. So the aim of this project was to generate and disseminate a 3D city model covering the whole of the Netherlands, and to do this in a sustainable manner with yearly updates, a close link to existing topographic registers and using an open standard. Now, where is this data used? Of course, there are many applications, but one very important application of 3D city models for us and the Dutch governments is noise simulation. Part of the data generated in this project was modeled in such a way that it can directly be used in studies about noise propagation. Then a few words about the scope of this project. Our 3D model is created from existing national datasets. On one hand, we have the 2D large-scale topography, and on the other hand we have point clouds, which are both LiDAR-based and image-based. Then we distinguish three parts to our 3D model. Firstly, there's a complete terrain model, which is a triangulated DTM of sorts, including LOD 1.2 buildings. Then there is a more detailed 3D building geometry layer, and this includes buildings in level of detail 1.3, more on that later. And thirdly, there's a detailed height statistics layer for the buildings delivered as a 2D vector dataset, as opposed to the previous layers, which were all 3D. Now this layer is mainly contains the different elevation percentiles for each roof part and the ground elevation. I will now quickly highlight the most important parts of our methodology, starting with the preprocessing of the 2D large-scale topography. This involves the discretization of arcs, resolving topological issues, and the removal of duplicate objects. Now this is needed because we sometimes find errors in the source data, and also to ensure that the software runs smoothly in the next steps. Next, we detect underground building parts. Now, since our elevation data only covers the above ground objects, we choose to remove the underground parts from buildings. And this is done by overlapping the building footprints with the ground points from the point cloud and then subtracting those areas. Then the terrain objects are generated using the 3Dfire software, which you can find at the following link. Now this tool combines the 2D vector geometries, you can see a cross section here, from the large scale topography with the elevation data from the point cloud. So to each polygon elevation is added, and how this happens depends on the object class. For instance, terrain polygons are triangulated while planes are fitted to water and road polygons. Then the neighborhood relations between adjacent polygons are determined and vertical faces are added to fill the gaps. The result is a watertight digital terrain model in which the individual input objects from the large-scale topography are represented in 3D. Next is the LOD 1.3 building reconstruction. In this phase, a more detailed roof geometry is computed for each building based on a building footprint and the matching building points. This is a 5-step procedure. In step 1, planes are detected in the point cloud. You can see the different planes with different colors in this image. In step 2, lines are detected from plane boundaries and the intersections between adjacent planes. Step 3 involves a footprint decomposition into the different roof parts based on the lines that were detected in step 2. Step 4 is the extrusion of the decomposed footprint into an LOD2 model. And step 5 is a generalization to LOD 1.3, where height jumps of less than 3 meters are removed. Now, one big advantage of this LOD 1.3 representation is that it can easily be represented using a 2D vector type in conventional GIS software, because each roof part has a constant height. Here you can see some LOD 1.3 results for the city of Rotterdam. To ensure that we have good insight into the reconstruction quality, we output for each building model the actuality of the point cloud. Was the building changed after the point cloud acquisition? Data coverage. How big are the parts where we have no point cloud data? Notice that these no data areas greatly affect the confidence that we have in the reconstruction, since the algorithm has no idea what a building should look like in an area where there is no elevation data. Then there is the root mean square error, which is essentially the error of the point cloud with respect to the building, the roof type, if a building is flat or not, and the geometric validity checked with our Val3DT software. And finally, an aggregation of all of the above into a single quality rating so that non-expert users can quickly get an idea of the general quality of a building. For the dissemination of the dataset, we use the open city JSON format. This is an alternate encoding of the CityGML standard. I will not dive into the details now, but you can read more about this standard on the cityjson.org website. And last but not least, we made an effort to integrate all of the processing steps into one automated workflow. To compute the 3D model for the whole country, we chose for a tile-based approach, where each tile is generated independently and in parallel. The output is stored in a PostgreSQL database from which the data is exported as CityJSON and offered for download on the periodical platform, which is our national SDI. Using this workflow, the dataset can be updated on a yearly basis. All the generated data is offered as open data on the periodical platform. Here is the download link in case you are interested, and also the link to the specifications of the dataset. We will continue to work on the further development of this dataset and the supporting tools. Big open questions are about combining different sources of elevation data to improve the actuality and on further aligning our efforts with 3D city models created by local Dutch governments. And independently from this project, our research group is working to release a national LOD2 building dataset soon as well. This will be the second version of the 3D Bach dataset that our research group maintains as open data, to be released in the coming months. Now, if you are still listening, thank you so much. I hope it was interesting and I wish you a good day.